Welcome to a presentation on TrueRMA, learning fast and smooth robot trajectories with recursive midpoint adaptations in Cartesian space. My name is Jonas Kiemel and this is joint work with Pascal Meissner and Thorsten Kröger from Karlsruhe Institute of Technology. So let's start with the motivation of our work. When a robot should interact with its environment during its movement, we typically know where the robot should move to and what the robot should do. However, finding a good trajectory with manual teaching techniques might be complicated, especially if the timing of the trajectory execution is crucial. As an example, consider a robot trying to balance a ball on a plate while moving between specified points. In the videos below, starting points and endpoints are randomly sampled within the black-edged areas, and our goal is to keep the ball as close as possible to the center of the red plate. Our question is, can we learn to generate such trajectories from data if we know where the robot should move to and what the robot should do? Problems like this are common in industrial manufacturing. Examples include welding, sealing, and grinding. Especially for industrial applications, trajectories are preferred to be fast, and in any case, the generated trajectories should be smooth. Generating good movements for tasks like balancing, welding, or grinding is challenging, since the performance of a trajectory depends on both its waypoints and its time parameterization. For instance, when trying to balance a ball, a straight line movement performs poorly, but if we adapt the waypoints a little, pretty good results can be achieved. However, if we execute a trajectory with the same waypoints faster or slower, the performance is once again poor. Considering all potential combinations of waypoints and time parameterizations leads to a huge search space. We tackle this problem by assuming that all trajectories are parameterized in a time-optimal way. Given a starting point and an endpoint of a trajectory, a neural network is trained to predict intermediate waypoints. Due to our assumption, a unique time parameterization can be assigned to each generated trajectory path. Talking about related work, collision-free trajectories in non-moving environments are typically generated by sampling-based motion planners like PRM or RRT. If timing matters, optimization-based planners like STOMP can be applied. In contrast to our work, STOMP doesn't reuse experience, and the generated trajectories aren't parameterized in a time-optimal way. In our approach, the desired starting point and endpoint of a trajectory are given as input to a neural network. The network outputs actions which are used to parameterize intermediate waypoints. We've investigated different techniques for waypoint parameterization, which will be explained later on. By adding circular planes around the waypoints, a smooth Cartesian path is generated. This Cartesian path is transferred to joint space by an inverse kinematics solver. Next, a time-optimal parameterization is computed and given to a joint trajectory controller. During training, the trajectory is executed by a physics simulator and its performance is rated with a scalar reward. Using reinforcement learning, the neural network is trained to generate well-performing trajectories. Waypoints can be defined in Cartesian space or in joint space. In Cartesian space, the position of the robot's effector is given by values for x, y, and z, while the orientation can be specified with roll, pitch, and yaw angles. In joint space, a waypoint is defined by one angle per joint. When working in Cartesian space, task-specific knowledge can be incorporated. For instance, in our experiments, the roll angle of the balance board is set to a fixed value. Another advantage is that the workspace can be easily restricted. On the contrary, special care must be taken to avoid singularities, and waypoint prediction in Cartesian space is not directly applicable to whole body control. The output of a neural network can be directly mapped to intermediate waypoints. In our simplified planar example, the x and y coordinates are predicted for each intermediate waypoint. In a final step, the path is smoothed by adding circular planes. With this technique, which we call TrueAbs, an untrained agent generates very long and poorly performing trajectories. It is also possible to define waypoints relative to each other by predicting the deviation to the previous waypoint. Once again, two parameters are required to define a waypoint in our simplified example. A random agent generates waypoints close to the starting point, as the predicted deviations cancel each other. Finally, a path can be defined by recursively predicting orthogonal midpoint adaptations. This way, only one parameter per waypoint is required in our simplified example, meaning that the search space of our neural network is narrowed. Having a look at a random agent, we can see that the intermediate waypoints are evenly spread between the starting point and endpoint. Once the path is generated, a time-optimal parameterization is computed considering joint velocity limits and joint acceleration limits. Time optimality means that at all times at least one joint is working at its velocity limit or its acceleration limit. Close to the starting point and the endpoint, the execution speed of this exemplary rollout is restricted due to acceleration limits. In the intervening time, the maximum velocity of joint 1 is the limiting factor. So let's compare how the presented techniques to define waypoints perform during the course of training. We start with the boundary hit rate, meaning the probability that the ball hits the black boundary of the balance board during trajectory execution. Given enough data, all techniques learn to keep the ball on the plate, but TrueRMA learns significantly faster. From a mathematical perspective, the goal of the training process is to maximize the average reward. In our experiments, the reward is assigned based on the average distance between the ball and the center of the plate. We can see that the best performance is achieved with absolute waypoint prediction, while TrueRMA converges against a lower value. In this case, the smaller search space of TrueRMA leads to faster learning at the cost of final performance. As shown in this figure, TrueRMA produces the shortest trajectories, which is reasonable as the search is guided by straight line movements. TrueAbs starts with very long trajectories, but finally learns to generate short ones. The same tendencies can be seen when comparing the mean execution time. The following exemplary rollouts further visualize our results. After being trained with 30,000 trajectories, TrueRMA generates well-performing movements, while both other techniques fail to keep the ball on the plate. However, after 120,000 trajectories, absolute waypoint prediction yields the best balancing performance. In summary, we presented a method to learn smooth and time-optimal trajectories which are optimized for a specific task. Moreover, we compared 3 different techniques to parameterize waypoints. While a balancing policy could be learned in all cases, TrueAbs achieved the best performance and TrueRMA was the most data efficient. Currently, we are trying to apply our method to more complex tasks, like balancing a ball while avoiding moving obstacles. The preliminary results in the videos were achieved by penalizing movements close to the obstacles. Keep in mind that these trajectories are fully specified prior to their execution. To allow online trajectory adaptations, we recently incorporated sensory feedback and transferred the resulting policy to a real robot. Have a look at our preprint on arXiv if you're interested. That's all for today. Thanks for your attention and goodbye.